And our next speaker, welcome, is Dr. Iona Sfampa, holds a PhD in physics from the Aristotle University of Thessalonica. And she's been working at Kleeman since 2016 as an innovation researcher and specialist in patents and intellectual property. And you're going to talk to us on design of a compact air conditioning unit using CFD and thermoelectric coolers. Thank you very much.
Thank you very much. I'm really happy to be here with you today. I've heard so many interesting things the last 2 days, and I hope that I will present something that may interest you. I will not use the podium because you keep reminding me that I'm short. Sorry. I'll try to be here so you can see me. I will say a few things how we came up with that project. Actually, it's a project that we have between our company and 2 universities back in Greece. And we have cooperation with 2 different departments, both departments of physics and mechanical engineers. The concept was that space means money, so you have to make the fullest usage of space. That's why the market of reduced clearances is raising the last few years. So if you want to add an air condition, but you have a headroom less than 30 centimeters, it's almost impossible to find an air condition that short. And if you have a beautiful mall, and you have a panoramic shaft full of glass, where will you put the air condition? It's not that beautiful looking at that. So we're trying to find a kind of air condition that it's really small, and you may put it somewhere hidden. Okay, my presentation will be in 6 steps, and let's start. First of all, I would like to explain you what the thermoelectric coolers are. Actually, they are based on the Peltier effect. It consists of N-type and P-type semiconductors. And when we have a direct current through these, one junction absorbs heat and the other junction releases heat. Okay? You have several factors that may affect their efficiency, but I will focus on the advantages. We have no moving parts, they are really small, they have precise temperature control, and they are environmentally friendly. You don't need any kind of refrigerants. Okay? And these are the reasons why the last few years they are used in electronics and in medical devices and etc. So this is how they actually look inside. We have P-type, N-type, okay? And we have like a sandwich of ceramic plates on both sides. But the project has to look into it, how many actually elements do I need? This is how they looked like in real life, and I have one of them in my pocket. It's that small, okay? So we were curious and we opened them. And these small things over here are the semiconductors that I already talked about. And you have the cables and you may connect them between them, okay? And then we followed up with designing a unit, a heat exchanger. How would that unit, that kind of air conditioner would look like? And this is it. And we, for the simulations, we considered a normal cabin, a widely used cabin dimensions, and we realized that if we need cooling power like 750 watts, you only need 10 of these, because each of them has the power of 75 watts. The dimensions of the unit is less than 30 centimeters, and the height is less than 10 centimeters, okay? And over there you have the pockets in order to add this, to install these elements, okay? The cell of the unit is aluminum, okay? And over here we have parallel fins, so the air may flow through these. So from one side, the hot air gets in, it's cooling down, and then you have the cool air from the other side. And in order to simulate would that actually work in real life, we had some kind of computational fluid dynamics analysis. We used more than 6 million finite elements in order to do the analysis, and we had 4 different cases. Combination of 3 different air velocities and 4 different cooling powers. And this is an example of them. Over here we have the velocity of 1 meter per second and the cooling power of 50 watts. What we can see here is that from this side the hot air is coming in and the temperature of this air is about 31 Celsius degrees. On the other side, we have the cool air getting out, and the temperature is almost 18 Celsius degrees. To sum up all the results, we have this diagram. So we can see that if we keep the velocity stable, as the cooling power is raising, the temperature is getting lower and lower. And we have the opposite effect. If we have the cooling power stable, as the inlet velocity getting greater, the temperature rises further. The results show that we are able to cool the air in a cabin, but how we would install it in an actual cabin. And this is what we propose. We install it between the ceiling and the false ceiling. So we have some kind of a fan over here that forces the air get inside it, and we have made the assumption that this is able to get about the whole air, the volume of the whole cabin air, about 4 to 5 times per hour. You can see that it fits perfectly here. You have already spaces, so the air flows through the cabin, and you don't have losses through the shaft. And our first try to actually make that unit was trying to make it through metal sheet, but we're not able to make them parallel. So the air was not able to flow smoothly. So next try was metallic 3D printed. Everything looked much better in this case, and we have perfect fins, and the whole shell, it's much lighter and better. To sum up, the unit looks functional, it's efficient, it's really small, so we may actually install it between the ceiling and the false ceiling. The air may flows freely, and it's modular. If you have a larger cabin, you may add more of these, or even add another unit on another corner of the ceiling, and it's kind of cost efficient. And I'm talking kind of course, it doesn't cost as much as a normal air condition, but the technology keeps going on, so we don't know the actual price of that right now. As I already told you, the project is between Cleman and 2 universities, and it's part funded from the European Union and the Greek government. And this is our team plus me. And thank you.
Questions?
What stops the thermoelectric cooling systems being used conventionally in rooms? Are they less efficient than conventional AC systems, heat exchangers?
They cost a bit more.
Oh, they cost a bit more.
Yeah,
but
they are already used, but they cost a bit more than a normal air condition with refrigerants and that stuff. Okay. If we want to be eco-friendly, we have also to think about that. It's more energy efficient, it doesn't use refrigerant, but it costs a bit more.
But I guess
For example, this one costs around €5.
I guess the biggest problem is, whilst in a room you will have a split AC system where you have the compressor outside and the unit inside. With this, it's very difficult to separate the heat and the cool on a wall, or it becomes much more complicated installing it, because in your case you've made isolation so that the heat goes into the shaft and the cooling stays in the car.
Yeah.
I'm just thinking
Maybe,
how
maybe,
practical.
maybe.
Yeah.
Maybe. It's probable.
Fascinating units. Just where does the heat go? That's what I didn't see in your. You're just cooling the air, but there must be something that gets quite hot, right?
In the shaft.
You just put the heat into the shaft.
Yeah.
Okay.
You take the cool air and you expel.
Which is what you would do with a typical cabin air conditioner in warm climates. Okay, good. I understand. Those are really amazing.
Thank you very much.
Thank you. Thank you for the presentation. It was a really interesting project. Just one question. Did you consider any structure interactions and any right quality repercussions for the design? Or just was only fluent, no coupling with structural analysis?
Right now we are implementing it in a prototype, and hopefully next year I will have results of actual usage. So.
Thank you very much.
Thank you.